Okay, so let's assume now that we have a position weight matrix, and which is this one, and we can scan a DNA, so to assess scores. We have shown that already in the previous class. Now the problem will be to define a threshold, and when a score is greater than this threshold value here, we assume that we have a binding site, and in locations that the score that we get is lower than the threshold, we assume that this position is not a good candidate for binding. So in general, I will describe some methodologies here that we define, that will help us to define threshold and also test hypothesis, and we will do that by using p-values. So again, let's assume that we have this position weight matrix. Again, it's a named matrix. The row names are ACGT, and the scores here, the values that we have in the cells of the matrix, represent the preference of the motif for the different letters. So for example, in the first position of the motif, we have a preference for C and slight preference for G, while we don't really have a preference for T. And in the second position of the motif, we have a preference for A and slightly for G, but not so much preference for T or C, and so on. So this is a position weight matrix. We have shown how to compute it, and we can use this position weight matrix, and let's assume that this has L positions here, and let's say that L equals to 5, to scan DNA and get scores. So for example, if we have this position weight matrix and we have to scan this DNA here, we start from the first position, we get the substring that corresponds to the 5 first positions. We get 5 because the length of the matrix is 5. If the length of the matrix would be 6, we would get 6, and so on. So we get the first substring comprises 5 positions, and we can assess the score of this substring by just summing up the respective values. So for the first letter of the substring is A, so we go to A here, and then the second is C, so we get this -1 here, and we sum up these numbers and we get the final score. And then we proceed to the second window, so this one, and we get a different score. So we can get all the possible scores for a long DNA. And now the question, the real statistical question, which is interesting for us, is what score is big enough to consider the location as a candidate. Probably I must say here that the greater the score, the more plausible the binding is. And so in real DNA we might have binding with different affinities. We don't really know, so we may assume that this affinity of a transcription factor, so a protein, if this is the DNA, the affinity of transcription factor to the DNA here is a parameter. We can call it binding strength or whatever. And this is an unknown parameter. So let's keep this in mind because we will need that later on. And different proteins bind to the DNA with different strengths, different affinities. Okay, so in order to find the score, we may explore two ideas. In both of these ideas, we need to compare the score that we get, so this value here, with some other values. So we will go by comparison. Now the first idea is to compare the scores that we get. So compare the scores here, the scores, with cases that we know that we have binding. Now if we know, for example, that when we have binding the scores are around, let's say 10, let's say that it's some distribution here and the scores when we have binding is something like that, then if we get a value, a score something like that here, let's say 10.6, then we say okay, it fits pretty nicely with the cases that we have binding, so probably my case is a binding as well. Now the second idea is to do exactly the opposite, to compare the scores that we have with cases without binding. Again, the idea would be the following one. If we know that when we don't have binding, the scores are around, let's say like that, this is 0.1, and our score is again 10.6, then we say, oh, look here, my value does not fit actually the distribution of scores when I don't have binding. So here is no binding, here is binding. Or in other words, in this second case, the probability to get a score of 10.6, so the score of 10.6, to write it precisely, I must write the probability to get a score S which is equal or greater than 10.6 when I have no binding. It's very, very small. So it's possible to get such a score, but the probability might be really, really, really small, something like 0.00001, for example. So again, I will stand a little bit on the second case. If we compare our scores, so the real score that we have is 10.6, with cases that we have no binding. Since a high score denotes binding in our case, indicates binding, we want to assess how possible is to get such a high score that we have observed, or even higher when there is no binding. If this probability is very small, then we will say that this model here of no binding, this hypothesis that we have, is not really able to produce such high values or even higher than what we have observed. So we have these two cases. There are actually methodologies that combine these two. Now I will demonstrate here that actually it's pretty difficult to use the first idea, so to compare our scores with cases that we have binding, and it's much easier to use the second idea. So let's see why this first idea is difficult. Now remember that we said before that a protein might bind to DNA with some affinity, which might be small, might be large, but it's a parameter, and this parameter is unknown. So this is difficult because if we want to compare our score with some binding cases, we have no idea what kind of affinity to use here. To compare it with cases with small affinity, or to compare it with cases of medium affinity, or with cases of high affinity. Even if we would know the affinity, it would be pretty difficult to find examples that have exactly medium affinity or high affinity or whatever. So the first case is pretty difficult. Now what I said affinity, I named it here strength of the binding. It's the same, I use the same term for both. Okay, the second case now is easier, because the affinity in this no binding case has an exact value, and the value is 0. So when there is no binding, there is no affinity, there is no strength of binding, everything is 0. Okay, that's much better now. We don't really have to consider different affinities. So we need to compare our value with what we expect when there is no binding and assess whether there is binding or not. Alright, so again the idea would be to, I just re-say the idea. The idea is to calculate scores in cases that there is no binding, and then compare our score with these cases, and if our score is much higher or much different, much higher in this case than what we get when there is no binding, then we say okay, it is possible, it might be possible to get such a high score or even higher when there is no binding, but this probability is very, very small, so I reject the hypothesis of no binding and I assume that my case is a binding case. In terms of probability, this is something like that, and if this probability is very small, then I assume that I have binding. Just to be complete here, the probability, the other probability that we need to assess here is the probability of getting such a score when there is binding. I have to think here if I have to write greater than 10.6. This is the Bayesian case anyway. We will not say much about the Bayesian case today, but let's focus on this one. Okay, now the question is, where can we find such a data set that there is no binding? Okay, so the question is how or where to find a data set that no binding is present. And now here we don't actually know for sure if a given data set, when I say data set I mean DNA string. If in a given DNA string there is no actually binding. However, we assume the following things. The first approach assumes the following. If we artificially construct, this artificial construct is another phrase for the word simulate. So if we simulate a DNA randomly, just by chance, then no binding will occur. Or if there will be binding, there will be in a very, very few positions. Now this assumption is valid because if we artificially construct a DNA, then probably it will be via some sampling approach where we will sample randomly letters, say CGT, and by sampling of these letters we will construct a DNA. Of course, we can sample with equal probabilities each letter, or we may sample with different probabilities every letter. Or even we may say, in order to keep some structure of the real DNA, that we will not sample single letters, we may sample dinucleotides, so AA, AC, AG, AT, CA, and so on. So sometimes we really want to sample something more complicated than just single nucleotides in order to resemble better the real DNA. We know that in real DNA the location or the positions of the nucleotides are not entirely random. So for example, it might be that 20% of the letters is A, 20% of the letters is T, 30% of the letters is C, and 30% of the letters is G, but the order of these letters is not entirely random. So here, to see an AT, the probability given these frequencies will be 4%. However, in real cases it might be that this will not be 4% but will be 6%. which means that there is an overrepresentation of AT. In other words, that when there is an A T prefers to be next to that. If this is something that happens in real DNA, then if we construct an artificial DNA just by sampling HCGT, then what we construct differs a lot from the real molecule because of these combinations of nucleotides. So if we will use this artificial DNA to compute the threshold, then the threshold might be very different in this molecule here than in real DNA. And therefore we try in the simulations to put as much real information as possible, keeping the interesting parameter at 0. So for us the interesting parameter is the affinity, is the strength of binding, so we will keep constructing the DNA randomly in order to minimize the probability to have a binding site here. Okay, this is the first approach. In a few words, the first approach says construct artificially with some stochasticity a DNA molecule where you don't really put any binding site there. Now the second approach assumes the following, that even if we have a real DNA, not artificial one, then the majority of this is has no binding. So we may have a DNA of 100 million base pairs, 100 million bases, and in this DNA here very few binding positions might be present, which means that the vast majority of this DNA contains no binding sites. Therefore, we can either randomly pick pieces from this DNA or scan this DNA with a position weight matrix, and the scores that we will get from this assume that binding is not present. Okay, in both of the cases, so either approach 1 or approach 2, we managed to get many scores that conditional on the hypothesis that there is no binding. In other words, we managed to get the probability of the scores, the probability distribution of the scores when there is no binding, or when what we say the null hypothesis H0 is true. So the null hypothesis in our case is that there is no binding, and we get the distribution of the scores, of the score values, when the null hypothesis is true. Okay, so this, if we're going to put now all these score values in a distribution here, we might have something like that, where here is 0, here is, I don't know, -5, and here is +5. And now, if we have a candidate score here, that this score we found it to be the score of the position weight matrix in a real DNA in position 3578, for example. Now if this score is somewhere here, it's very high, so let's say that the score is 4.9, and from this distribution there are only a few values that are higher than 4.9, and the probability of these values, so the probability to obtain a score higher than 4.9 when the null hypothesis is correct is small, and this is smaller than 0.05. Then we say that we reject the null hypothesis and we accept the alternative hypothesis, which is that in this position there is a binding. So what we have done in this hypothesis testing is the following. We have this score that we have taken it from this position. Okay, so we have applied the position weight matrix here and we calculate the score, and this was 4.9. And now we assume that this binding position comes from the null distribution, from the null hypothesis, which means that this position here is not a binding site, but it's a location that has been actually obtained from this probability distribution. Or in other words, it's a location that has been obtained either by a random DNA that we simulated, or by the vast majority of the real DNA that there is no binding. In either case, we assume that this binding site here, that this position here is no binding position, is a no binding position. But if we assume that this position is a no binding position, we know what kind of scores to expect, because we know the distribution of the scores in the null hypothesis, and it's this one. Okay, and if our value is somewhere here, 4.9 for example, then we say, okay, it is possible to obtain such a score when the null hypothesis is true, but it's not so possible. It's actually extremely rare. The probability to obtain such a score is less than 0.05. And therefore we reject the hypothesis that we did, that this binding site has been obtained from a null hypothesis, so from a hypothesis of no binding, and we accept the alternative hypothesis that this position here is a binding position. Okay, so this is the hypothesis testing. Now the threshold for this probability is really what we use in biology, the 0.05. Later on I put an asterisk here because we will talk about multiple hypothesis testing. That actually we should apply in our case, but we will see that later on. And now let's see in the code how to find such a distribution. What I must also say here before going to the code is the following. Here we are interested for scores that are greater or equal to 4.9. So we are interested for this really. We are interested in this inequality because we know that when there is binding we expect high scores, and we want to assess how possible is to get so high scores or even higher when there is no binding. Okay, there are other cases that we don't really interested only in the direction of higher than, but different than. As an example, let's say that we want to assess whether two populations, population A of people and the population B, have people of the same height or not. So our null hypothesis here is that the people from the two populations have the same height, or in other words, that the two populations do not differ from each other considering height. So the difference in height, let's call it D, equals 0. Now this is the null. You see again that we have a specific value for a parameter. Now the parameter here is the difference in mean heights in the population, mean height, so me1 and me2, and we construct this parameter which will be the difference of these two values here, two parameters. So this is the mean value in this population and this is the mean value in this population, and this parameter has a value 0, a specific value for the null hypothesis. And then if we get a sample from here and a sample from here, let's say N1 individuals and then 2 individuals, we can actually have ways to construct the distribution of this D. So D will be now the difference of the samples, M1 minus M2, and from this sample consists of N1 individuals and these N2 individuals. We can construct the distribution of this D when the null hypothesis is true, which means that when the real means of the populations are equal. Okay, so this will be the distribution of this D under the null hypothesis. And now, since we are interested if these two populations are different or not, considering height, we are interested either in when D is very positive. So if we have observed the D, let's say that our observation of D is 3.7 centimeters, so that this population A is the sample that we got is 3.7 centimeters higher on average than the sample from the second population. So this is actually that M1 minus M2 is 3.7. Now we are interested either when we observe in the null hypothesis such a difference or higher, so this is the 3.7 here, but since we want to answer the question whether the two populations are different in height, we must think the following. Now if this is the value of that we have observed, the M1 for population 1, and this is the value for M2, to make the populations different needs this distance to be high. Now this distance is not just the difference M1 minus M2, it's actually the absolute value of M1 minus M2, which means because the absolute value between two numbers is actually the distance of these two numbers. So we want to know how possible it is to get such a big distance or even greater when the null is true. Okay, which means the following, that we must assess the probability to get this greater than 3.7, which means that either this M1 minus M2 must be greater than 3.7, which is a probability for that when the null is true, so in this distribution, or the opposite, like minus M1 minus plus M2 to be greater than 3.7 when the null is correct, or in other words, M1 minus M2 smaller or equal to the minus 3.7 when the null is true, which means that we must add in this probability, which is this one here, this one as well. So if the alternative, so it's really important to know what is our alternative hypothesis. Here our alternative hypothesis is to find a score which is strictly greater or equal to 4.9, because if we have binding then we have large scores. Here our alternative is that this distance must be large, because the larger this distance is, the more dissimilar the populations are. So we want to assess the probability to find such a big distance or greater, so 3.7 or greater when the null is correct. And this distance here translates to M1 minus M2 or M2 minus M1, which means that we should check both of the edges, both of the ends of the distribution. Some other times we are interested only in this part, if we want to test whether a value is smaller than some threshold when the null is correct. Okay, so I hope it was clear why we do hypothesis testing and how we do it and why it's useful for us to do hypothesis testing when we search for thresholds. So this was the theoretical part, and let's go now to the practical part in order to see how to do that for position-weight matrices. Okay, so we have seen several of these things in the previous class. So here I have two position-weight matrices just to demonstrate that the score might be different for different position-weight matrices. So let me reconstruct them. Okay, so I have two position-weight matrices. The first one, this PWM, is this one. You see it has relatively not very large positive values, and it has some negative values here, some positive, quite positive as well here. This means that we don't really have strong preferences for some nucleotide in some position. Okay, and the PWM2 in contrast is a bit different. In some locations at least, there is a very strong preference. Like in the first position here, there is a strong preference for A. In the second position, there is a strong preference for C. In the third position, there is a strong preference for C as well. In the eighth position here, there is a strong preference for G, and so on. So these two matrices differ in their quality, and we will see if they really behave differently in a random sample of DNA. So we said in the theoretical part that we must construct a DNA artificially, and this DNA will just be a stochastic, will be emerged. We will obtain it from a stochastic process where we will just sample randomly ACGT letters in order to construct something that we don't expect to find any binding position here. Okay, so this DNA, if I execute this command here, now the DNA is this 20,000 random letters. We said in the theoretical part that it might be not very good idea to construct this DNA sample just using an ACGT alphabet. Perhaps it would be a better idea to construct by using D nucleotides, which will be, I will not write all of them now, but it will be this collection here, A, G, and so on, up to TT. Now, if these dinucleotides have different probabilities, then we might construct, randomly simulate a DNA sequence that, at least in some features, is more close to the real DNA than what we construct here by just sampling a letter every time. Okay, in any case, we have the random sequence of DNA, and we have said in the class how many scores we expect to find. We expect to find as many as the length of this DNA is minus the column of the position-weight matrix plus 1. Okay, so we construct this vector because it will be much faster to put the values here. And then here I don't have a function to find the scores. I just throw 2 for loops here and I find all the scores. So this is all 19,900 something scores that we get for the first position-weight matrix and the DNA sequence, and we can find the distribution of these values just by using the hist function. And we observe that the majority of these scores is really negative. Okay, 0 is somewhere here, a few values is positive. Now, if this distribution if we want also to illustrate it as a what we are using as a distribution here, we can use the density function. So plot density all scores will be something like that. And now we're going to find the threshold, and the threshold will be a value. So the threshold here will be a value on this axis where the 95% of the values of this distribution is below the threshold. In other words, only the 5% of the values is higher than this threshold. For example, if this score is here, if this threshold is this 5.1, let's say, then if we get a score that is higher than this 5.1, it means that its p-value will be lower than 0.05. Okay, let's see this in paper just to make it clear. So this is a distribution, as we saw, of the values when the null is true. So I just try to imitate this distribution here. So 0 is something like here, and 5 is here. And we get a value, and we calculate that the threshold is 5.1. So 5.1 corresponds to the top 95 of the distribution, or in other words, there are just 5% of the values that are higher than this 5.1. So this is 0.05. Why this is a threshold? It's a threshold because if we get a value higher than 5.1, let's say 6, so 6 is here, this probability is definitely smaller than this probability. So the probability to obtain a score which is higher than 6 given H0 will be definitely smaller than the probability to obtain a score that is equal, greater or equal to 5.1 when the null is correct. Okay. However, this is 0.05. By construction here, we said that all this is 0.05, which means that this number here is smaller than 0.05, which means that if we get a value that is higher than this threshold, we will reject the null hypothesis. I hope this is clear. Now let's find this threshold. It's pretty easy actually. We get all scores, we sort them, there are two ways. One is a manual way. I will show both of them. Sort the scores. Okay, now this is from the smaller to the greater, and we need the 5%. So how many values we have here? What is the 5%? It's the length of all scores multiplied by 0.05. This is something like 1000 values. Okay, 999.55 values. Okay, so we want actually to obtain the value that corresponds to this index in the sorted array. Remember that the sorted array is from the smaller value to the greater value. So we have an array that is something like that. Minus, let's put minus 11, minus 10.9, and so on. And let's say that goes up to score 9 here, 9.1, and then 9.15, and so on. And all of these values are, let's say, k. and these values are sorted. So in order to find this value here, which is the threshold, it means that here we have the 5% of all these values. So this will be the k multiplied by the 0.05, which means that all these values are k minus k 0.05, or in other words, this should be something like 0.95 of k. So the index here will be in this position of 0.95 of k, where k is the length of the sequence. Okay, it's the same thing that I wrote here. So the interesting index, our index, threshold index will be 0.95 multiplied by this number. And because this might be a non-integer value, we can actually be a bit more strict and find the ceiling of it. Ceiling means the following, I will explain it. So if this 0.95k will be a number, and let's say that this number is something like 18,083.3, I'm going to be a bit more strict and say, okay, my threshold will not be the 1880.83, but will be the 1880.84, because I have this 0.3 here. So I go to one value on the right, one index to the right. I go to the next position actually. And if I apply the ceiling function to a floating point number, let's say to the 10.1, then this will give, the next integer will be 11. Okay, so ceiling of this number, I get the threshold, and now sort all scores threshold index. Remember, you must have a sorted vector to do that, and that's why I use a sort function. It's a 2.8, which means that the threshold here in this distribution is a 2.8, somewhere here, which means that this probability here is exactly 5%. Or in other words, if I have a value which is greater than 2.8, this will lead me to reject the null hypothesis and accept the alternative. So this is a manual way to find the threshold. Another one is to use a function quantiles, or it's quantile. Let me see. Yes, quantile, and the vector is the all scores. I don't need to sort it now, and I'm interested in the 0.95 probability, and now it's 2.82. You see, it's a little bit different because this quantile function here uses a little bit better math than what we really did, but these two numbers are really close. So use whatever you prefer. This is slightly more correct mathematically. In any case, our threshold value is around 2.8. So this is a way to find thresholds using the concept of p-values. I hope that all the concepts were clear. Thank you very much.